Assalamualaikum and hello everyone. In this presentation, we will discuss the application of ordinary differential equation in pollution control. I will start by briefly explaining what pollution is before moving on the mathematical model. First of all, our group consists of 3 students which are Nur Arif, Muhammad Nazrin Hakimi and Zahirul Hakimi. Pollution is the contamination of the environment such as air, water and soil, and it is mainly caused by human activities. In daily life, pollution commonly comes from industrial waste, vehicle emissions and improper waste disposal. These activities release harmful substances into the environment. Pollution is a serious environmental issue because it can negatively affect human health, damage natural ecosystem and reduce overall environmental quality. For example, air pollution can cause respiratory problems, while water pollution can affect aquatic life and water resources. Therefore, understanding pollution is important before discussing methods to control and manage it.
Let's start by looking at pollution as a problem that changes over time. Pollution doesn't stay constant, it's constantly increasing and decreasing. For example, it increases due to human activities like industrial production, transportation, and waste disposal. At the same time, natural processes such as wind, rainfall, sunlight, and decay help to reduce pollution levels. Because pollution is continuously changing, we need a way to study it over time, not just measure it at a single moment. This is where mathematical models become useful as they allow us to understand and predict the behavior of pollution over time. This brings us to ordinary differential equations or ODEs. ODEs are tools that describe how quantities change with respect to time. In the case of pollution, instead of only knowing how much pollutant is present at a single moment, ODEs help us understand how fast pollution is increasing or decreasing. They are particularly suitable for continuous process like environmental change, where additions and removals happen simultaneously. That's why ODEs are widely used in scientific studies, environmental engineering, and pollution modeling. They give us a systematic way to predict trends over time. Now, let's see how ODEs specifically relate to pollution. In any environment, pollution is constantly entering from human activities and leaving due to natural process. ODEs allow us to model this balance, capturing both the input and the removal at the same time. By using these equations, we can predict how pollution levels will evolve. For example, we can estimate whether pollution will continue to rise, decrease, or stabilize at a certain level over time. This information is extremely valuable for environmental planning, helping policymakers and engineers design effective strategies to control pollution and protect our environment.
Now, we will go to a problem statement. A lake initially contains 20 kg of pollutant. Pollution flows into the lake at a constant rate of 5 kg per day from nearby factories. The lake has a natural cleaning process that removes pollution at a rate proportional to the amount of pollution present, with a proportionality constant of 0.2 per day. Firstly, find the expression, and second, the amount of pollution in the lake after 5 days. So here's the first problem solution. The solution is quite similar to the mixture problem, which is dA over dt equals to rate of inflow minus rate of outflow. But this time, we are using the pollution inflow and the pollution outflow in the lake. So, first of all, we need to list all the given information, which is I will let AT equals to amount of pollution in kg at a time t, which is days. So another information given is A0 equals to 20, which is the initial value. So this problem already give the value of dA over dt for inflow and the dA over dt for outflow. So we don't need to calculate the value of dA over dL and dL over dt. So dA over dt for inflow is equals to 5 kg per days, and dA over dt for outflow, which is 0.2A, or we convert into the fraction, is equal to A over 5 kg per days. Since the problem is using the concept of mixture problem, which is dA over dt equals to rate of inflow minus rate of outflow, we will get the equation of dA over dt equal to 5 minus A over 5, and then we derive the equation, so it will be like the linear differential equation, which is LDE. So dA over dt plus A over 5 equals to 5, and there is a value of P and Q. So the value of P is equal to 1 over 5 and the value of Q is equal to 5. After that, we need to find the integrating factor, which is the integrating factor is equal to exponential power of integrate P dt. So we must substitute the value of P, which is 1 over 5, into the integration. So it will be exponential power of integrate of 1 over 5 dt, and we will get the value of integrating factor is exponential power of 1 over 5 t. So after that, we will use the formula, which is A times IF, integrating factor, equals to integrate of Q times integrating factor dt. So we will substitute the integrating factor in the equation and the value of Q. So it will be A times exponential 1 over 5t equals to integrate Q, which is 5, times exponential 1 over 5t dt, and we will get the result of the integration is equal to 25 exponential 1 over 5t plus c, and then the value of at the left side, which is A times E 1 over 5t, we must let the A stand alone, which is A equals to something. So we will get the value of AT is equal to 25 plus C times exponential power of negative 1 over 5t, and then we already got the value of we already got the expression for the this equation, and then we have something missing, which is the value of C. So by using the initial value, we will substitute A0 equals to 20. So 20 equals to 25 plus C times exponent power of 0, and we will get the value of C is equal to negative 5, and then we will get the expression of the amount of pollution at a time is equals to AT equals to 25 minus 5 exponential power of negative 1 over 5t. Okay, so for the second solution is we need to find the amount of pollution in the lake after 5 days, right? So here's the second problem solution. So 5 days means the 5 is the value of t, right? So we need to find the value of A, and the value of t is already given. So A5 equals to what? So we just need to substitute the value of 5 into the equation, which is the value of t. So we will get a5 equals to 25 minus 5 exponential power of -1/5 times 5 times t, which is we substitute the t with 5. So we will get the value of a is equals to 23.16. So the units of the a is kilogram. So we will get the value of a after 5 days is 23.16 kilogram. So that's it.
In conclusion, ordinary differential equations provide a powerful way to study and predict pollution in the environment. By modeling how pollution enters and leaves a system over time, ODEs help us understand whether pollution levels will increase, decrease, or stabilize. This type of modeling is essential for planning effective pollution control strategies, protecting air and water quality, and supporting sustainable environmental management. In short, connecting ODEs to pollution allows us to turn real-world environmental challenge into actionable insights.